Hello my dear students, welcome you all to the new lecture on module 2. There is a second unit on unsteady state or transient heat conduction. Okay. So the contents which will be covered under this presentation is topic level outcome, syllabus of this unit, definition of transient conduction, application, concept of lumped heat analysis, a very important derivation we are going to do here. There is only one derivation in this unit. So to derive expression for temperature and heat transfer rate, under the derivation we are going to define two new concepts, that is Biot number and Fourier number and characteristic length. The topic level outcome here, very important. There are two topic level outcome. At the end of this chapter you should be able to apply the concept of lumped heat analysis for the given problem. It is mainly to find temperature at any given time t, and to solve the second one, solve the transient heat conduction problem to find out temperature at given time and space both. This is using a Heisler chart or Grober chart we call it as. Okay, thank you. The syllabus which will be covered under this unit is given here. The transient heat conduction definition in different cases. One is negligible internal thermal resistance or negligible surface resistance, both are same. That is called as lumped heat analysis. That is nothing but BI less than 0.1. And second one is comparable internal thermal and surface resistance, that is called Biot number greater than 0.1. Okay, so only two concepts here we are going to study and numerical problems. Now let us see what do you mean by transient or unsteady state heat conduction. Okay, we will start with an example. Now you can see here a plane wall which is maintained at temperature 15 degree and 7 degree centigrade. Let us take Q1 is the rate of heat transfer. This is at time 2 pm. Now at time 5 pm it is observed that temperature remains same at 15 and 7. So the heat transfer rate Q2 also same as Q1. This is called steady state heat conduction, where the temperature and heat transfer rate remained same with respect to time. Now another application, if you see here, same example, but just see at time 2 pm the temperature is 15 and 7, but at time 5 pm after 3 hours temperature dropped from 15 to 12 and 7 to 5. Now the heat transfer rate also, initially it is Q1, at 5 pm the rate of heat transfer is Q2, which is not same as Q1. Now what happened here is the temperature at a given point on these surfaces changed with respect to time. Simultaneously the heat transfer rate also changed. This is called as transient heat conduction. Okay, therefore I can define transient heat conduction as a heat conduction where the temperature will vary with respect to position and time. Temperature is function of both space and time. So the definition goes like this: the conduction of heat in unsteady state refers to transient conditions wherein the heat flow and the temperature distribution at any point of the system vary continuously with time. As simple as it is. Transient or unsteady means temperature and heat transfer rate vary with respect to time. Now let us see the applications of these. There are various applications. Okay, and even in household we have a mini system where the temperature with respect to time matters. For example, even in the cooking process, the design of utensils, gas stoves, the rate of burning, the rate of flame, intensity of flame matters a lot. You can control the intensity of flame, you can vary the time. Okay, and then we have refrigeration system. Iron box is a very good example, where if you control the rate of heat transfer, the ironing time also can be controlled. Okay, so temperature at any given time. Then we have IC engines, cooling of IC engine, automobile engine, heating and cooling of metal billets, refrigeration, as I told, cooling and freezing of food. A very important application is heat treatment of metals. A very crucial for all mechanical engineers. You are supposed to know this, and it depends upon the concept of transient heat conduction. Okay, then the heat exchanger process. The entire heat, the rate of flow of fluid, hot and cold fluid in a heat exchanger, it controls the timing of heating. Okay, so the starting and stopping of the various heat exchanger units. Okay, then we have brick burning and vulcanization of rubber. So the lumped heat analysis, let us now go into what we mean by lumped heat analysis. Again, we have two examples here. The first one is a roast beef. You can see here, when it is started to heating, okay, you can see the outermost temperature is very high, but as you go inside, the temperature drops. The inner core, the temperature will be less compared to the outer surface, correct? So here the temperature is varying with respect to position, and if you continue the heating, the temperature will go high, but it will not be same throughout the body. Take another example, a copper ball, a small copper ball heated. Here temperature remains same throughout the body, okay, it is 70 only. If I continue heating, the temperature increases, but it will increase throughout the body uniformly. So therefore I can tell that the case 2 here, temperature is function of space and time. This is a true transient heat conduction problem, whereas the first example here, temperature is function of only time. With respect to space, it is same. Okay, this is called as lumped heat analysis. That is what explained here. Therefore I can tell the special case of transient heat conduction as a lumped heat analysis. So the definition goes like this: in heat transfer analysis, some bodies are observed to behave like a lump, just like this copper ball, whose interior temperature remains essentially uniform at all times during heat transfer process. The temperature of such bodies can be taken to be a function of time only, T is equal to T. The heat transfer analysis that utilizes this idealization is known as lumped system analysis, which provides great simplification in certain classes of heat transfer problems without much sacrifice from accuracy. So many transient heat conduction problem can be simplified to lumped system analysis. Here temperature is variable of only time, so which can be easily solved. Okay, that is what the concept of lumped heat analysis. It is also called LHA many times. Please remember that. Now what is a condition? This is a very important. So the first condition, we already know that temperature should be uniform throughout the body. This is possible only if two conditions should be met. One is thermal conductivity of the material is very high. Second one, surface area is large compared to volume, that is metallic wires, sheets, etc. Okay. So when the surface area is very high, what happens to the resistance? It means L by Ka. When K is very high, L by Ka will be small. It means thermal resistance for conduction is negligible. It's almost like there is no resistance offered for conduction. When there is no resistance offered, there is no temperature gradient, there is no temperature difference within the body. That's why you will get uniform temperature distribution. Therefore we can tell that the lumped heat analysis is a case where thermal resistance for conduction is negligible. That is what explained in the first content. Okay, different case, negligible internal resistance. Therefore there is no temperature gradient. Therefore any system can be considered a lumped heat analysis only if its thermal resistance is very less, negligible, and that is possible only if the thermal conductivity is very high and surface area is more. So the application of LHA is, it's there in heat treatment of metals, time response of thermocouple and thermometer. So how quick a thermocouple or thermometer can read the temperature, it can be easily explained by lumped heat analysis. Okay, now let us go to the derivation of T of T. Very important derivation, is the only derivation we have. Consider a solid body. You can take an example of a potato which is boiling in the water. Okay, if you take the solid body as a potato, it has a mass m, volume v, density rho, and surface area a. Let us take Ti is the initial temperature. It is kept in a surrounding hot water. Let us take the surrounding temperature is T infinity, heat transfer coefficient is H. Okay, as the time increases, temperature will go on increasing. Now what happens is there is a heat into the body, going into the body by convection. Okay, so applying energy balance equation, now what I can tell is the rate of heat entering into the body must be equal to rate of increase in internal energy. This can be easily explained by this. h into a into t of t infinity minus t into dt. Why dt I have taken is the convection is in watt, joules per second. I want to know how much heat has entered into the body in time dt. So dt, that is equal to increase in internal energy, mcp dt. Mass is nothing but density into volume. Now if I rearrange the term, if I take all the temperature to the right hand side, remaining term to the left hand side, I will get HA by rho Cp into dt by T infinity minus T. Here I will get I have to introduce this negative sign here, because if I differentiate T infinity minus T infinity is constant, I will get minus dt. So that sign is introduced and it is rearranged, T minus T infinity. So if I continue with that, now I have to integrate both the term. I have to integrate time from 0 to t and temperature from Ti to t. Okay, now integration of dt is nothing but t. Integration of the right hand side here, it is 1 by x into dx integration, that is ln x. And if I put the limit, so I will get this term, ln of t minus t infinity by ti minus t infinity. If I take ln to the left hand side, I can write t minus t infinity by ti minus t infinity equal to e power minus h into a into t by rho cpv into v. Cp is the specific heat. So I can find out temperature at any given time t if the surrounding temperature is known, initial temperature is known, and all these constants are known. Now we will introduce some of the very important terms, okay, variable. First one is the thermal time constant. See, if you see this HA by rho CPV, if you see this term, if you substitute all the units here, H is watt per meter square, A is meter square, density is kg per meter cube, specific heat is joule per kg Kelvin, V is volume. If you substitute, you will get the unit is 1 by second. Okay, it has a dimension of inverse of the time. Therefore, the reciprocal of this HA by rho CPV, that is rho CPV by HA, has unit of time. Therefore, it is called thermal time constant. Therefore, I can write the same expression T minus T infinity by Ti minus T infinity equal to e power minus T by tau thermal. Okay. Now this graph I can easily explain, since this expression contains exponential term. Okay. The heating or cooling process can be defined as Newtonian heating or Newtonian cooling. That is, during the heating or cooling process, the temperature varies exponentially. Okay, that is what explained in the graph. Suppose if I take heating process, if Ti is the initial temperature, which is very less, okay, as the time goes on, temperature also increases exponentially. Similarly, cooling process also exponential. The second graph, transient temperature response graph, shows the importance of thermal time constant. If you see, as the thermal time constant increases, okay, the time taken to reach to a particular temperature also increases. If you see this line, when the thermal time constant is low, the first line T1 is the time taken to reach to a particular temperature, but for the third thermal time constant to reach to the same temperature, it takes more time. Okay, therefore if the thermal time constant is higher, the time taken to reach to a particular point is also higher. This concept is used in design of thermocouple, okay, or thermometer, to find out the response time. Thermocouple or thermometer should give the response time as early as possible. It should record the temperature as early as possible. Therefore, this graph is explained. Now we will find out another term here. In the term HA by rho CPV, the volume by area is called as characteristic length, because the unit of volume is meter cube, surface area is meter square, meter cube by meter square you will get meter. This is called characteristic length. Okay, and this characteristic length, the value of characteristic length is different for different geometry. For example, flat plate, it is given by L by 2. so half of the thickness. For a cylinder, if you substitute volume and area, you will get r by 2. Sphere, you will get r by 3. Okay, this value you should remember while solving the problem. So we have to consider the value for characteristic length. Similarly, for the cube, it is L by 6. Now another term we will introduce here, that is Biot number and Fourier number. Same time, HA by rho CPV into T can be rewritten like this in terms of two number, HLC by K and alpha T by LC square. Here alpha means thermal diffusivity, which you already know, K by rho C, LC is characteristic length. Now the first term HLC by K is called Biot number, and the second term alpha T by LC square is called Fourier number. Okay, we will explain what this number in the later lecture series. Now you remember HA by rho CPV into T is called Biot number and Fourier number. Therefore I can write the final expression as T minus T infinity by Ti minus T is equal to e power minus HA by rho CPV into T. This can also be written as e power minus Bi into F naught. In terms of thermal time constant also we can write, which we have already seen. Now the last part of this, that is heat transfer rate during transient conduction. The instantaneous heat, there are two types of heat transfer rate we are going to derive. One is instantaneous heat flow rate and there is total heat flow rate. Okay. Instantaneous heat flow rate means during the entire heating process from time t equal to 0 to t, if I want to know in between or at any time what is the rate of heat transfer, that is called instantaneous. Okay, but if I want to know from 0 to t what is the total heat supplied, that is called total heat transfer rate. So the instantaneous heat transfer rate is given by using this expression rho Vc into dt by dt, and the temperature expression is written like this: T is equal to T infinity plus Ti minus T infinity e power minus HA by rho Vc into T. This is based on the previous equation we got. Okay, now you differentiate the entire term here. Here T infinity is constant, so it is 0, and only you have to differentiate this e power. So e power minus mx, differentiation of e power minus mx is e power minus mx into m. So if I substitute, what you will get is Qi is h into a Ti minus T into e power Bi into F naught. This is called instantaneous heat transfer. Very important, its unit is in watt. Similarly, the total heat transfer rate, now I can find out, that is from 0 to t, total how much, that is obtained by integrating instantaneous heat transfer. 0 to, it's not tau here, it should be t. Substitute the Qi value here. Okay, now all these terms are constant, only you have to integrate this time variable. This should be t. Integration of e power minus mx, we already know integration of e power minus mx by minus m, that is what we get here. Put the limit 0 to t, and if you put the limit here, the final expression you will get like this. Okay, so the total heat transfer rate, now you can see its unit is in joules, rho Vc Ti minus T infinity into e power minus Bi into F naught. Now you need not worry about this expression because it's already there in the data handbook, so need not by heart. Only thing you should know this derivation. Okay, yes, now we have come to the last part of this, that is summary of lecture 1. So therefore at the end of this presentation we have learnt what do you mean by transient heat conduction. Okay, temperature is function of space and time. Then we have studied the special case of transient heat conduction, that is lumped heat analysis, that is temperature is function of only time. And we have derived the expression for temperature, T minus T infinity by Ti minus T infinity equal to e power minus HA by rho CPV into T. It can be written in the form of dimensionless number, Biot number and Fourier number, and also we can write in terms of thermal time constant. What is the importance of thermal time constant? We have seen what is characteristic length, two numbers, and finally we ended up with the deriving heat transfer rate, instantaneous heat transfer rate and total heat transfer rate. Okay. So if you have any questions, please post in the Google Classroom or Telegram chat section that we have. So with this we will conclude the first lecture. We will see you all in the lecture 2. Thank you.